Okay, so we'll start with Dr. King's.
Oh, got the big dark side.
It's not too dark, I think. Do you guys feel it's too dark? Are you okay with that?
That's cool. Is that okay?
Yeah, it could be even better than dark.
You want more?
No, I don't need more.
A bit darker. A little darker.
Oh, yeah. Yeah. Glad you're here. There we go, that's fine. Down is fine.
Keep it dark.
There you go.
That's, yeah.
Thank you. I'll keep an eye on my time to make sure I don't go over.
I can run the controls if you
Yeah, no, cool. So is done.
want.
All right, forward then. Okay, perfect, cool. Okay, very glad to see everyone this morning, and welcome to Dallas, and let's hope we have good eclipse viewing. Yeah, although fingers crossed.
Dr. King has been here for more than 10 years. I know because I took her class here. She's been lecturing about astronomy and physics. And one of her students told me recently, and I agree with this, that she's a person that really cares about the student and the people and what they learn and know. So we're very fortunate to have her here with us this morning.
Oh, thank you. Thank you for the kind words, and also, yeah, thanks for inviting me to speak. If I say anything which is like confusing, maybe just interrupt me, right? Okay. So I'm just gonna kind of get situated first. So as you know, the Milky Way is 100,000 light years across or so, and contains several hundred billion stars. And Andromeda, as you'll all know way better than I do, is about 2.5 million light years away. So it's like just thinking about these distances is huge. And that's actually very close, astronomically speaking. So the objects that I study are on the whole way, vaster distances. And so the universe has been growing for about 13.8 billion years. So there's so much for us to observe and to try to understand. Okay, so I'm gonna give you an overview of some of the research I'm actually working on. And one of the things I work on is trying to understand how did structures in the universe form? How did they evolve? Like over those 13.8 billion years, where do we get all the galaxies and all the galaxy clusters that we see in the sky? And one of my main techniques for that is something called gravitational lensing. And so a big thank you to gravity, because without gravity, like most of my work wouldn't be possible. And then I'm also going to talk about collisions between massive galaxy clusters. And so what happens if massive galaxy clusters undergo collisions? And then finally, I'll talk a bit about what can we learn from gravitational lensing, but of gravitational waves rather than electromagnetic waves. So rather than lensing of like radio or, optical light that we currently are studying. Okay, so basically a brief history of what's going on with the universe. So the universe, we think, started about 13.8 billion years ago with something called the Big Bang. And then the early universe was so hot and so dense that, it was just like a giant plasma. And not even photons could travel. So, radio waves couldn't travel. Nothing was kind of able to travel. And eventually, as the universe expanded, it cooled down enough so that the protons and electrons of, the hydrogen, which makes up most of the normal stuff of the universe, could recombine. And then at that point, photons were free to travel. And that's about 380,000 years after the Big Bang. And then what we then see from that epoch is the furthest radiation we can directly see that we measure with microwave telescopes, and that's called the cosmic microwave background radiation. So if we look at this cosmic microwave background radiation, and we look at the temperature fluctuations in this radiation, it's very, very smooth. So all of the pictures that you'll see of the cosmic microwave background are greatly like enhanced in their, to show tiny, tiny, tiny fluctuations. And so we know then at that time that everything was very smoothly distributed with only a few kind of like small scale blips. But over time and under gravity, those small scale fluctuations that we see on the cosmic microwave background would grow and form all the massive objects that we see today. So on the top right, we have just a box out of a cosmological simulation. And this is like on a loop. But what you should see is that at high Z, meaning like early in the universe, things were kind of more spread out. And over time, like structures are forming like as time goes on. And what is shown here is like snapshots out of at different times, showing that early in the universe, everything was kind of pretty smoothly distributed. And then eventually galaxies and galaxy clusters form, right? So all of this is like gravity is essential in all of these processes. Okay. So just a little word about gravity. So we all know the story of like Isaac Newton and the apple tree, right? And so Newton's ideas on gravity, were very important, and a lot of like, Newton's ideas then were later developed by people like Einstein, giving us the concepts that we have of gravity today. And okay.
Another plastic experiment. Well, on my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Okay, and so like that confirmation, so work of Galileo, work of Newton, then actually led on in the 1900s to work of Einstein. And so Einstein determined that if I have a massive object like the Earth or a black hole or the sun, then mass actually curves the space-time around it. So what actually then Einstein concluded is that this curvature of the space-time by massive objects is responsible for what we interpret as gravity. And why that becomes important is that Einstein calculated the angle by which he expected light to be deflected by a massive object. And so for something like a star, like our sun, then the deflection angle, so if I have a distant source and the light is coming along and it gets deflected through some angle, that angle of deflection is going to be proportional to the mass of the object and inversely proportional to the distance away from the object. So that deflection of light by an object is actually what during the eclipse of 1919, when Eddington and other groups of investigators looked at the apparent shift in the locations of stars behind the sun, and then they found like values for that deflection angle, which were in keeping with what Einstein was predicting. So that deflection of light by stars is like a consequence of Einstein's theories. Okay, and so what I need to say for going forward with my talk is that now, by now, we have many astrophysical data sets. So the cosmic microwave background, how structures in the universe have grown, and lots of astrophysical data sets point towards a picture of the universe where all this kind of like gray region is dark, either dark matter or something that we call dark energy. And the colored regions here, shown in yellow and red and green, are basically stuff that we know. So stuff like protons and neutrons and electrons, and the remnants of, of dead stars or any kind of gases we have in the universe. So basically the known sector of the universe only makes up maybe 5% or so of the contents of the universe. And so most of the matter in the universe, as I'll speak in a moment, is in the form of dark matter, and that doesn't directly emit any radio waves or any optical light or X-rays or whatever. And then we think that a larger part of the universe is in the form of something which I'll call dark energy, and that is leading to the present day observed accelerated expansion of the universe. So without dark energy, we wouldn't be having the observations, for example, of distant supernovae, which show the universe isn't expanding and slowing down, but it's actually accelerating in its expansion, which suggests there must be something beyond the gravity of matter in order to make that so. Okay. So the classical evidence for dark matter came already in the 1930s from Fritz Zwicky. And Fritz Zwicky looked at the Coma galaxy cluster and saw that the galaxies in that cluster were moving around much more rapidly, that if there wasn't an extra source of gravity, they would be flying away from the galaxy cluster and wouldn't be gravitationally bound. So from the motions of galaxies inside Coma, and from observations made by or pioneered by Vera Rubin of like spiral galaxies, where what Vera Rubin measured was that clouds of gas are actually moving faster as we go out to the edge of a galaxy rather than what we'd expect if dark matter wasn't present. So in other words, to provide the gravity either to keep galaxies bound to a cluster or to have stars or gas moving very rapidly in the outskirts of galaxies, we need some extra source of mass. And so we think now about 80% of the matter in the universe is actually dark matter. Okay. So this diagram kind of summarizes our ignorance of dark matter. So this kind of like the sector in here marked like protons and muons, neutrons, and so on, can be accessed by either looking at electromagnetic waves, so like radio waves, for example, or now by looking at like gravitational waves. So we have access by observations of this luminous sector, directly. But this other kind of blue region out here is our dark matter region. And one of the main candidates for dark matter is something called a WIMP, which is a weakly interacting massive particle. But the Large Hadron Collider has been searching for, what makes up these WIMPs, what WIMPs actually are, and hasn't yet found, the identity of dark matter. So there are other possibilities, we're studying things like axions, we're studying other particles, which might be, providing the properties that we need dark matter to have to reproduce the observations we make of the universe. So one way to access this dark sector comes back to what Einstein predicted would happen from the bending of light. And so if light rays are bent or radio waves are deflected, then in a gravitational field, we're also going to get something called gravitational lensing. So if we imagine light traveling from a very distant galaxy, and it travels past a massive object, which is distorting the structure of space-time, like Einstein, said would happen, then those light rays or radio waves are going to get focused to us. And as we observe here on Earth, we are going to see either multiple images of distant sources or maybe slightly distorted images, depending on the exact strength of that deflection. And so what is super important is that the deflection that we see and those gravitational lensing effects, the gravity is caused by dark matter and by luminous matter. So even a blob of dark matter is going to cause gravitational lensing. And so even if I had a giant clump of dark matter sitting somewhere in the universe, it would produce those same deflection effects and reveal itself because of this gravitational lensing. And so here, I'm showing a few examples of systems that I have been involved with of these gravitational lensing systems. So I'm just going to point out, for example, this system, where those two blobs, this is a radio map made using the Merlin array in the UK. Those two blobs are actually multiple images of the same original radio source. And on the sky, these two blobs are separated by about 1/3 of an arc second. And so the separation on the sky also lets us know about the actual like mass of the object, which is doing the gravitational lensing. So for something like a galaxy, the sorts of separation on the sky we get of images is going to be of order an arc second or less, or maybe a little bit more. So somewhere between a fraction of an arc second and an arc second and a half or so. And then, so this example here, again, something you wouldn't see intrinsically in nature is a Merlin map of a radio map that I made many years ago of a distant radio source, which has two initial components. And one of those components, like this one sitting here, actually has another corresponding image, which you see like up above. And then this like arc-like feature is actually several radio components all seen on the sky. And then we made a map of the same object using the Hubble Space Telescope NICMOS camera. And what you'll see with the Hubble Space Telescope image compared with the radio image is that there's this giant blob in the center of that image. And that is basically because in the radio image, we don't detect radio emission from the foreground galaxy acting as a lens, but in the Hubble image, we see emission from the galaxy because of the wavelength of the radiation, which the thing is emitting.
This picture up here on the left is causing the arc. Is that dispersion or is that some gravitational effect?
Yeah, so the picture on the left, great question. The two like eyes, the two like bright spots are foreground galaxies. And then all these like extended features, all these arcs are distant galaxies, which have been stretched into arcs because of the gravitational lensing. So these weird features like the stretched out arcs are caused by the foreground gravitational field. And in this case, we ended up calling this one Mr. Smiley, but those kind of like extra features are because of gravitational lensing. And similarly, these like arc features here, this I'm extracting from a Hubble Space Telescope image, are also caused by the foreground galaxies causing the lensing. Okay, and just to quickly show, this is the locations of the telescopes, the radio telescopes in the Merlin array. And for example, I did my graduate studies actually at Jodrell Bank, so University of Manchester, but I got the chance to live walking distance to Jodrell Bank, which was so cool, which was really amazing. And then other telescopes I've used include the one at Cambridge, where I was a undergrad, and then I was there later on. And so another radio telescope I've used is the Very Large Array in New Mexico, and that's also very, very cool. So using these very long baseline radio telescopes like Merlin, or very long baseline interferometry, where there's even longer baselines than in Merlin, you really see very, very fine structures in objects. Okay, and then this just shows our radio map superimposed on top of the Hubble image, where we can then see this is the foreground galaxy, which actually caused that weird looking radio source. Okay, so one very cool application of gravitational lensing is to actually to see the most distant galaxies in the universe. So this field is the first James Webb Deep Field. And what you can see here are many examples of gravitational lensing of distant galaxies. And people like Tommaso Treu and colleagues in UCLA actually looked at these images, and they looked at tiny blips of light that really looked like little blobs. And they determined that some of those blips of light are some of the most distant galaxies we've ever seen. And without the magnification of gravitational lensing, some of those galaxies would not be seen. So if they're magnified by like 10 or 20 or 30, then gravitational lensing also acts like a natural telescope, allowing us to see objects which we wouldn't actually perhaps see. Okay, and then here I'm going to talk now, go to talk now a little bit about galaxy clusters and colliding galaxy clusters. And I'm going to talk a little bit more about gravitational lensing, but also about some other observations and other interpretations we can make. So what is shown here is the bullet cluster, which you might have seen. And this is work by Douglas Clow and collaborators. I was a postdoc in Bonn at one point, and I shared an office with Douglas Clow, and Doug actually discovered the bullet cluster. And I remember he came, showed me this like gravitational lensing map, these like contours that you see here. And he said to me, this is very strange, like, look at where the mass is compared with where the X-ray emission is. So I thought that was cool, because that was really where he realized there's something very weird with this object. So what is going on here is that two very massive galaxy clusters, and galaxy clusters are, most of their luminous matter is in the form of a low density plasma, and that plasma emits X-rays, naturally emits X-rays. And then a few percent of the mass is in like stars and galaxies and so on. But most of the luminous matter is actually emitting X-rays. And so when two objects collide, dark matter mainly only experiences gravity, whereas if I have a plasma, then I experience like other forces. You know, we get in a plasma, we would get things like shocks and, you know, so on. So we get other, we experience other sorts of physics besides gravity. And so what's happened here is that the two objects have passed through each other. And what's shown in the colored emission is the X-rays from the plasma. And so the plasma is actually lagging behind most of the mass. And so here you can see this feature, which kind of looks like the wake of a bullet. And this is why this is called the bullet cluster. And so these components are, one is moving in this direction and one is moving in this direction. But where we map most of the gravity is not associated with where the plasma is. So these peaks here represent the peaks in the gravity where we don't see most of the luminous emission. So that tells us that gravity, given us this gravitational lensing reconstruction, that gravity must be coming mostly from dark matter. And so Doug and his collaborator said this is like direct evidence for dark matter. Okay, and similarly, we have observed another system called ABEL 2146. And something similar, we have a galaxy cluster down here and a galaxy cluster up there. And those clusters are now moving away from each other, having passed through each other. And just to show you, we have done a multi-wavelength campaign on this particular system. And so here up on the top left is an X-ray image of this system. And that was taken with Chandra X-ray Observatory. And that is work led by Helen Russell, one of my collaborators. And then we have direct optical images using the Subaru telescope on Hawaii. A direct optical image, which goes out further than our Hubble image does. And we also have optical from like Hubble Space Telescope. And then here, what is shown in these contours is a reconstruction of the total mass that I have made and some of my, my collaborators have made of where is the total mass in this system. And what we can see is that most of the mass, like the contours, are peaked around here. And then there's also, a peak up here. And then that would correspond to, for example, also what we see in the radio in work led by Julie Hlavacek-Larondo, who's in Montreal. This is showing here, this would correspond to this component and this component in the radio in her VLA image. And so we can piece together what's going on from Chandra, which shows us the plasma in the system. With the optical information, one of my former undergrads did an analysis similar to Fritz Zwicky, where he looked at the motions of the galaxies using like optical spectroscopy. And then we can also, look at the total mass. And this information allows us to reconstruct what is the history of, this object, and allows us to make computer models, which I'm not actually showing here, but which seek to reproduce these observational features. And so these objects are very rare, but since galaxy clusters are the most massive objects in the universe, it's very cool to understand, like, how do those massive objects interact with each other, and how do they evolve? And then super important is that by looking at the total mass from gravitational lensing, we can compare that with what we see directly from the plasma and what we see directly from the optical, and understand that most of the mass in this system is actually dark matter. Okay, those are details, but we'll go into how we did some optical stuff on that. Okay. I will now talk a bit about gravitational waves, and if I have time at the end, we'll come back to another galaxy cluster system. But so now I'm thinking about the what is accessible since 2015 with gravitational wave observations. So as you know, in 2015, the first detections of gravitational waves were made from merging compact objects. And that is by the LIGO, like two experiments here in the US. And so that network is also being added onto by other telescopes around the world, making like what's called the LIGO Virgo CAGRA like experiment. So one thing I'm particularly interested in, and the European Space Agency is very has like really promoted the Linsay mission, which will be a space-based gravitational wave mission, and also NASA has involvement in that mission. And as well as probing the stellar mass black holes that we can see with LIGO, which stellar mass black holes should be like everywhere in our our galaxy and other galaxies, but supermassive black holes that live at the hearts of galaxies, like our own supermassive black hole at the center of the Milky Way, if they are merging, then we need a different kind of detector in order to see the radiation from merging supermassive black holes. And what's particularly interesting for me is that with Linsay, the sources that we expect to see will be much more distant than possible with LIGO. And the further away a source is, then the bigger the probability something is going to be in the way to act as a gravitational lens. Does that make sense? So if I have a source at a redshift of 10, or one of the most distant sources, there's more probability there's going to be something in the way to make to do gravitational lensing. So when you think about the lowest frequency radio observations, gravitational wave observations, the wavelengths involved of gravitational waves are even longer than the longest wavelength, like radio observations. So very long wavelength. What is very interesting about these sources is that they are very coherent. So the emission is very like well-defined in wavelength or well-defined in frequency. And they are naturally time varying, because as black holes like in spiral, then the pattern of signal that we see is going to be like varying in time as, their frequency gets larger as the objects kind of like get closer and closer. So the one thing you'll have heard about gravitational wave observations is that there's very poor sky localization. So if you go and look at a radio source, pretty well where on the sky it is. That like if you're looking in that direction, then it's not likely that your source is over in that direction. But with gravitational waves, like they're very poorly localized, so they might detect a signal, but at the moment the uncertainty on the sky is very poor. But they do have great resolution in time, so measurements in time have very good temporal resolution. Okay, so here, so similar to what we mentioned, like masses creating like dents in space-time. So similar to that, similar to how gravitational lensing works, if we have merging supermassive black holes or merging compact objects, then those masses are accelerating around each other. And another consequence of like Einstein's theories, another possible solution is a gravitational wave solution. So basically objects which are emitting gravitational waves, very massive objects as they go around each other, are going to be sending out ripples into space-time. And the ripples that they send out into space-time like carry signatures about their masses and the properties of those objects, right? So we also think that gravitational waves will have arisen at the time in the very early universe of inflation, when the universe like very rapidly expanded, but those have not yet been detected, but we've detected now signatures of merging objects and and their gravitational waves. So anyway, why this is interesting to me is that, and just very quickly, sorry, this is to show here we have frequency in hertz. And so this is like 10 to the 6 hertz, so like a 1 megahertz over here. And down here we have like super low frequencies. And what is being observed at the moment, the LIGO coverage covers these sorts of frequencies around here, starting at around 20 hertz or so. So by the time, we get over seismic noise, starting around 20 hertz. And then something like a LISA experiment. And what is shown here is the characteristic signal and frequency. So in other words, if a signal is larger than these curves, we would expect to detect it with that experiment. So with LISA, compared with like LIGO, so LIGO coverage is over here. And so LISA coverage is at lower frequencies, so larger wavelengths even than LIGO. And the frequency range that LISA covers will be able to see things like supermassive black hole binaries and other, very interesting objects that aren't accessible with LIGO. Okay, so for me, what we have been making predictions for, and this is work supported by the National Science Foundation. So here, as my source, instead of having an electromagnetic source, we have a gravitational wave source. And so here then, we would have some kind of like gravitational lens, like a galaxy or something. And what we are showing here is I've plotted how, remember we said that massive objects distort the space-time. So here, this kind of like graphic I've shown is actually for a simple model of a lens. Literally, this is like how it distorts how time is looking around that particular object. So this time delay surface, we can plot for different kinds of lenses. And here I'm just showing a simple model of a lens. And that simple model of a lens results in 2 images of that gravitational wave source. And what is like super important, remember I mentioned that the radiation from these gravitational wave sources is coherent. So meaning that it's very sharply defined in frequency. So although frequency changes with time, the frequency is pretty sharply defined. And that means that unlike, if I'm in this room and I had like 2 light bulbs close together in this room, I wouldn't be able, I would just see it as like a single blob. Whereas with coherent radiation, what we can get is interference between like different coherent signals. And so if our gravitational wave signal is changing in time, and if those signals are taken slightly different times to arrive at us because of gravitational lensing, then the signals actually interfere with each other. And what I show here is the gravitational wave signal as a function of the frequency. And this is drawn just for a LIGO source. And here, this orange line represents the approximation to what the signal would be like if we didn't have gravitational lensing. So plotted in the frequency domain, what the signal would look like if we didn't have gravitational lensing. So the in spiral part of this like black hole merger. But when we have multiple images, and if those images take like a different time to arrive, then those are going to like constructively or destructively interfere. And so that means that then with gravitational lensing, we get this modulation of the waveform, and that modulation will depend upon what the gravitational lens is actually doing. So we're pretty excited about this. So then now I'm showing a slide from one of an undergraduate who works with me, SARA. And what SARA has done, and she illustrates this very nicely. So she has a lens and the observer, and she has a gravitational wave source, and she has like images. And, you know, these images take different paths to get to us. And Sarah's been doing some wonderful work. She has extracted lenses, so galaxies from cosmological simulations. So one of those structure formation things I showed you early on, where objects were forming, you know, in the universe, Sarah extracts galaxies from those simulations. And what she's showing here is what is the impact on those like light arrival time if she has offset supermassive black hole, which is not quite at the center of the galaxy. And then in this example, what she's doing is she is increasing the mass of the black hole. And I think you can see from this set of contours to this set of contours, you see like a change in these in these contours. And then in the top panel, she has an example like without an offset supermassive black hole. So basically, this is to say that using like galaxies extracted from simulations, we can see whether do we expect supermassive black holes in galaxies themselves to be contributing to what we observe when we look at these sorts of interference patterns. And this is her next step, is to make these plots of the interference patterns. Okay, so I think I am nearly out of time. And so I'll just wrap up. And so takeaways would be that gravitational lensing is a really great tool for looking at objects in the universe, both to study dark matter, most of the universe, mass in the universe is dark, and to magnify objects that we wouldn't ordinarily see. And then we can do, like I showed in the example, multi-wavelength observations going all the way from radio up through X-ray. And they give us different sorts of information about like objects like galaxy clusters. And then finally, I think an important point is that making predictions for gravitational lensing, but with gravitational wave observations. So currently with electromagnetic lensing, we have many hundreds of examples of like lens sources. And so, you know, going forwards, there's aims to search for similar for gravitational waves. And then, as I mentioned, gravitational waves being coherent, we're going to get different signatures compared with electromagnetic lensing. And those signatures, but some of the work that we're doing at the moment, for example, is to say, oh, if I had dark matter and it wasn't made of WIMPs, if it's made of something else, then how would that manifest on the sorts of like interference patterns that we see? So yeah, gives us a different view of the universe. Okay, and so finally, I have gone out of my slides. Sorry about that. Okay, so just finally. Yeah, sorry about that. Okay, so finally, what do I want to say? Let me go to the very last slide. It's not going forward, so it seems, okay, finally. Okay, so finally, thank you for your attention on a Monday morning, and have a really great conference, and hopefully, oh my gosh, yeah, oh Lord, we need to do some sunshine dance or something, right? And hopefully we'll have good weather come back again for the eclipse. Thank you.
Thank you. There any questions from anybody from here in Dallas or online?
Yeah, so, you know, I've seen arguments about the, relationship between the amount of force there is between like the electron force and the magnetic force in a wave. Then you've got the gravity forces in here, it seems to be on a much smaller scale. On the other hand, they're coming from very large masses that are more important maybe to the universe.
Yeah. So you're right that like in terms of like the structure formation, like the large scale things like assembling over time, like you say, gravity. If I in my electromagnetism class, I would have calculated like the relative strengths of electromagnetism and gravity. And so although like you say, gravity is going to be very important for assembling objects. But when we get to smaller scales, like if I'm calculating something on a very local level, I would be more concerned with like electromagnetic forces, right? So our like fundamental forces, like the gravity in terms of cosmology, is kind of the thing we would start with when we're doing simulations. But then when we get to things like actually how is star formation going inside galaxies or what other processes inside objects, then we need to do other physics like involving like star formation and formation of supernovae and so on. So the gravity is kind of like the stuff that builds the scaffolding and builds the cosmic web. And then we need other things, other physics going on inside to really describe the luminous contents as well.
Now, presumably at the time of the Big Bang, gravity was pretty much equal in all directions. What started that process of condensation that leads us to the cosmic microwave background?
Yeah, so it's thought that, and I have a slide somewhere else which I can show you later on, but it's thought that very early on in the universe there were tiny like quantum fluctuations, like very, very, very tiny fluctuations. So even those tiny fluctuations and also the fluctuations then that we see on the cosmic microwave background, where the variation is something like a part in 10 to the 5 or so from place to place. But if I guess because we're waiting for, you know, billions of years, that if we do a computer simulation and we set it up even with tiny fluctuations at that time, then just because of gravity, things can kind of like hierarchically kind of like, you know, come together to form like galaxies and then galaxy clusters and so on.
Have we found that magic variable that we can set that chaos kind of a portion of it to, that allows us to simulate more precisely or less precisely what we see in the universe?
So really, to be honest, because the furthest back we directly see is the cosmic microwave background, then that early kind of universe, like the inflation part of the universe, there's so many theories still that would be viable. And so, yeah, the things that we can really like get access to would start at the cosmic, like with what we can test from the cosmic microwave. Yeah, but there have been other, you know, from when inflation was like added to the Big Bang, for example, to account for some of the problems in cosmology. But still, there seems to be a vast number of possible like explanations for the you know, a big number of inflationary models. So the kind of like standard picture is that, oh, we had like quantum fluctuations. We see from the cosmic microwave background what at that time, 380,000 years after the Big Bang. And then if you do a computer simulation with that kind of distribution of mass and let it evolve, then it very nicely reproduces the structures that
We
we
can
see.
at least start at the cosmic background and get to where we are
Yeah.
today. It's going before that.
Yeah, exactly.
So can I comment on that too? 10 years ago, I remember you talking about the Hubble constant, how, everything's expanding.
Yeah.
Argument about whether or not it's just going to continue to expand.
Yeah.
Or is it going to come back around and collapse back down?
Yeah,
And there was a lot of science going into trying to quantify the Hubble constant. I guess that's all still big argument, right?
yeah.
From what you're saying.
So people now, so I guess, so with the Hubble constant, there's also now seemingly discrepancies between, so what Bob is talking about is like Hubble's work of the velocity of a galaxy being proportional to the distance. And that proportionality constant is like this Hubble constant. And when local measurements are made using like Cepheids or, even using like supernovae, the value that they tend to get is different than the value that you would get if you use like objects which are further away or using like the cosmic microwave background and so on. And so they call this like the Hubble tension. But the difference in the values compared with what it was, some decades ago, where people were arguing between like 50 and 100. So we seem to be somewhere settled around like 70 as a value. I would say that our best guess at the moment for what the universe is going to do in future is that it doesn't look like it's going to recollapse. It looks like it's going to somehow like expand forever in some sort of way. And so that would, I say, be at the moment like the standard picture based on all of the observations that we have. But there are still puzzles, like big puzzles. We don't know what dark matter is, which is like a big thing, given that it makes most of the mass. This dark energy, like one possibility is it's something called a cosmological constant, which originally like Einstein kind of dismissed and said it was his biggest blunder, but then it turned out to be something, which we do think is a good model. But we don't know, like from theoretical physics, we can accurately predict this cosmological constant. People are out by many orders of magnitude, people like Stephen Hawking's group in Cambridge trying to make predictions out by many, many, many orders of magnitude. So I think our understanding of most of the universe is still very poor. But I don't know, but it's exciting. So there's still many open questions.
I have
two areas of observation. One is fundamentally electromagnetism, Mr. Maxwell. The other one is gravitation, gravity. From what I have perceived, the two things are quite two different methods. To what extent is this correct?
Yeah, no, that is correct. So you're very correct. There are like analogs you can make between, like you say, Maxwell's equations describing electromagnetism, and then like Einstein's equations, like sourcing gravitational waves. And so they are very different, like very different processes. And so that I think is why it's kind of exciting. There was an analog of like, if you go into like a rainforest and you're walking through the rainforest, and what would be the difference if you could look and see, like you're going around, but you're wearing kind of like earplugs or something. And then like with gravitational waves, it's kind of like being able to hear as well as like see what you see in the rainforest. So I think they offer very complementary views of the universe. I think that's very fair to say. Stuff like, actually, interestingly, supermassive black holes, for example, unless they are, unless we have like an active galaxy or something like a quasar, they are pretty difficult to see, unless they're kind of actively doing something. And so the gravitational waves offer a nice way to access, properties like their masses and spins and so on. That so sometimes with electromagnetic observations, like for black holes, we can get information from things like X-ray measurements and, like the iron K alpha lines, particular lines that we can observe. But yeah, the gravitational waves, I think you're right. It's like very complementary to the electromagnetic information. And so I, worked for a long time just with electromagnetic stuff. And now this like NSF project I have with the collaborator, he is an expert on gravitational waves and black holes and things. And so that's very nice for me because I get to learn also about like gravitational waves. Yeah, never too late. Yeah.
So my question is, we're a bunch of amateur radio astronomers, which has some relationship to amateur radio. And I've noticed that most, especially in the electromagnetic, the work has been 100 megahertz and above because of the ionosphere blocking the lower level stuff. Now that we have the International Space Station and microcube satellites and all this stuff, and also looking at it separately as amateur radio astronomers, what can we do to participate in and move forward the science? What's your opinion of working, especially since LIGO is working in the below 100 megahertz range, of actually figuring out how to do electromagnetic work in the below 100 megahertz range?
So I guess that would be very, like, to have as much coverage as possible would be very, 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 very cool. And I know from talking with Bob, for example, there are many things that you're all doing, and I'm thinking, wow, that's very cool. Like experiments that.
Because we have very small radio
Yeah.
telescopes.
Yeah. So I think someone who is actually doing radio, like, doing actual work from is Fabiano, who will be speaking later on, I guess, from Space Sciences. And he is also like an expert on things like the ionosphere and so on. And so he, I think, will give you a much better answer than I could to that question. But from what Bob was saying, like people building antennae and things like the LWA, these like long wavelength arrays. Those I think are also like very exciting and can be used to do things like like observing pulsars and those sorts of things. And I know all of those measurements are very important for there's this like pulsar timing arrays that people are doing. So that I think it would be, well, yeah, it is very cool. Like understanding the arrival times of pulsar signals, and then if gravitational waves are passing through, then that would like disturb that. I was very impressed at what Bob was telling me about, like tracing meteors like coming through the atmosphere. So that is like super cool and something I hadn't thought of.
One thing that I think is important to think about for us in particular is like an amateur radio. You get a radio and you make a contact with somebody, and so it didn't take you very long. It's a big feat for you. But in astronomy, the work she's showing you right here has gone on for years.
Yeah.
Many years in some cases. So she got very focused on one thing, and that's what we could do. Pick something that's very interesting. You have to be very focused and diligent, take a lot of data, spend a lot of time staring at the data, thinking about what did you get to be successful at the long time.
Yeah, I think that's a very good, and like I would also say to, Bob, sometimes like all the sorts of things going on near to Earth, like I know way less than
you know, so yeah, like, and people had asked me, yeah, like questions about kind of near Earth phenomena, which, yeah, I'm very, like, limited knowledge.
You're near Earth, to her is a long way from.
And Fabiano, I think, will have much better, yeah, answers on that.
Well, thank you very much.
No, thank you, thank you.
Dr. King,